Imagine if you could hide secret messages inside an image. The image doesn't look any different, it looks like any other normal image, but it actually has some data hidden inside it. And no, I don't mean literally writing your data on the image using a photo editing software and messing up the colors so that the text goes invisible and doing some hacks like that. But what I mean is actually encoding some data into an image such that the encoded image looks no different from the original image, but the message that is encoded into the image cannot be retrieved unless you perform some scanning in a particular way, or in other words, decode the image. This is called steganography. It is a technique of hiding a secret in an object that is in plain sight, like an innocent image for example. This has been used in many places including internet mysteries like the Cicada 3301. In this video, I'll show you how to actually do this, and I'll be writing code in Python to implement image steganography. Also, in addition to just encoding the data into an image, we are first going to encrypt the data with a key or a password, so that when you want to retrieve the hidden data from the encoded image, you need to decode it first and then also decrypt it to its plain text form using the password. So let's get started. Every image is built with pixels. Each pixel contains a set of RGB values, which stands for red, green, and blue. These values indicate how much amount of red, green, and blue that the particular pixel must display. Our goal is to modify these RGB values such that we don't change them too much, but we also manage to include the given secret message in these values. The reason why we don't want to change these RGB values too much is that the encoded image must look the same as the original image. And if you change the RGB values too much, it changes the colors in the image, which brings a noticeable change to the whole encoded image, which we don't want. So here's what we're going to do. We take each character in the secret message and then convert it into its ASCII format. We then convert this ASCII value into its binary equivalent, which can be represented in 8 bits. Now we need to incorporate these 8 bits in the pixels or the RGB values. We need a minimum of 3 pixels where each pixel contains 3 values: red, green, and blue. So the total number of RGB values 3 pixels would contain is 9. So we take 3 pixels for each character in the secret message, and the first 8 RGB values of these 3 pixels combined are used to store the character, which is in an 8-bit binary format. We just compare the corresponding bit and the RGB value. If the bit is 0, we need to make the corresponding RGB value even. If it's already even, we make no modifications, but if it is odd, we simply add 1 to that particular RGB value so that it becomes even. Similarly, if the bit is 1, we need to make the corresponding RGB value odd. If it's already odd, we obviously make no modifications, but if it is even, we simply add 1 to it so that it becomes odd. In this way, we can incorporate these 8 bits into the first 8 RGB values. But we still have one RGB value left, which is the 9th one. We will use this as a termination indicator. We will make it odd if the message ends here, and we will make it even if there are more characters following the current character. So we are making use of this to indicate us whether the message ends here with this character or if it continues. And that's how you encode a text into an image. Now that we figured out how to encode some text into an image, how to actually decode the image and retrieve the hidden text from it. Simple. We know that each character is represented by 3 pixels combined. So we take 3 pixels at a time and build the binary from the first 8 RGB values. But how? If the particular RGB value is even, it means that the corresponding bit is 0. And if it is odd, it means that the bit is 1. Based on this logic, we can simply build the binary. We then convert this binary into its ASCII value and then finally into the actual character. Now we look at the 9th RGB value, which is, as I said, a termination indicator. If it is odd, it means that the message ends here with this character. And if it is even, it means that we should continue scanning the image. So we go to the next 3 pixels and repeat the same process. That's how simple it is. Now, as I said, we are also going to include some security by first encrypting the message with a password by using AES 256. Instead of encoding the plain text, we are going to encode the encrypted text or the cipher into the image. So this means that when you decode the text from an encoded image, it is still encrypted. Hence you will need the password to decrypt it into its plain text. So now that we figured out how to both encode and decode, it's time to write the code. So there you go. There is the working Python program. Let me show you a small demonstration. I'm going to hide some text in this image of two cute puppies. All I have to do is input the file path and extension of the image, and then input the message that I want to hide. And finally choose a password to encrypt it using AES 256. The encoded image is saved in the PNG format. Same way, you can also decode the text from this encoded image using the same Python program. Simply select decode in the options, enter the path of the encoded image and type in the password, and the hidden message will be displayed on the terminal. Since we are only dealing with RGB images here, this method only works for images that are in RGB mode. So keep that in your mind. And for the source code, check out the description for the GitHub repository link. So thanks for watching this video, hope you liked it, and if you did like it, please don't forget to leave a thumbs up below and also leave a comment in the comment section. If you haven't yet subscribed to my channel, subscribe now and also turn on the bell icon to receive instant updates about my new releases. Thanks for watching once again. I will see you in the next video. Until then, cheers.